Everyone. I'm so pleased to welcome you to our third webinar of the 2025 series. My name is Satwinder Paul. I teach in the Water and Wastewater Technology program, and with a team of experts and co-creator, I oversee the online help center for BC Small Water Systems. Before we begin, I'd like to acknowledge that Thompson Rivers University campuses are on the traditional lands of Tecumseh, Swetmik, and the Tikselek within the Swetmik Ulu, the traditional and unceded territory of the Swetmik people. Thompson Rivers University and Online Help Center host an annual webinar series and free courses dedicated to providing technical information, resources, and tools to all small water system owners and operators and Indigenous small water systems on issues of treatment, regulations, operations, maintenance, and water quality monitoring. We will have an hour of presentation first, followed by half an hour of question period. During this duration of the presentation, if any questions arise, please jot them down, and then we'll make sure that we address all your questions at the end of the presentation. I am so pleased to welcome my learned colleague. He has stepped in at the last minute because our previous scheduled webinar had to be sort of pulled out of the queue because some issue arose with our original presenter. So our webinar will focus today on fire flow testing of hydrants. It will cover the fire flow requirements from the Fire Underwriters Survey, how to do a fire flow test of a hydrant, and how to interpret the results of the test, as well as National Fire Protection Association color codes for hydrants. Our presenter is Scott Jameson. Scott is a graduate of OUC. He graduated in 1996 with a diploma in water engineering technology. He holds level 4 certification in water treatment, distribution, and wastewater treatment. Scott runs Jameson Water Services Training Organization out of Victoria, BC. He provides hands-on training and consulting services in the operation and maintenance of water and wastewater systems. He also is my colleague and teaches at Thompson Rivers University in the Open Learning Program. Welcome, Scott, and thank you so much for stepping in when we desperately needed you. So I'll let you begin your presentation.
Welcome everyone to this presentation on, on fire flow testing of hydrants. Now I know for some of you, or maybe a lot of you, this may not be completely applicable. You might not have a lot of hydrants in your system, or as you find out, you might not have enough reservoir capacity to actually do a proper fire flow test. But it is something important to at least conduct for your system and have some ideas on the hydraulic capacity of your system. So we'll run through the procedure here, and once again, as Satwinder had mentioned, if you do have any questions, please put them in the chat, and we'll get to those at the end of the presentation here. So for fire flow testing, once again, it is a way for us to look at the capacity of our water system and how that capacity might meet the requirements that are for fighting a fire in our system. So the testing for the fire flowing is not that complex, but it does require some equipment and some testing to done for the system itself. The first thing is the Fire Underwriters Survey. This is the organization that the insurance companies use just to try to be able to determine what is the water supply requirements for a system to be able to capably fight a fire. Now, we're going to go look at real quickly a formula that they use, but there are a couple of little benchmarks that we look at inside of the Fire Underwriter Survey. So the first one is this point up at the top there, is that at the very minimum, your water system needs to be able to provide 1,000 liters per minute for 2 hours. Or conversely, 2,000 liters per minute for 1 hour to effectively fight a fire. So right away, that comes out to, that we have to have a storage capacity of, 120,000 liters just to meet the very, very bare minimum for the Fire Underwriter Survey. Now, once again, then that might already eliminate some of your systems as far as your reservoir capacity or your pump capacity that you have available to you. Now, there is an actual formula within the Fire Underwriter Survey that we can look at here. I'm going to skip by that one. We're going to go to this one here. Also, one of the parts of the Fire Underwriter Survey and then the fire flow testing is what is the pressure in your water system. So the higher the pressure, generally the more water we can move throughout the system, and that's why a lot of small water systems may be installing fire pumps as part of their system, so that at those points when we need a lot of water in the system, we're able to push it out of our reservoirs and get it down to where it's needed. Now, one of the key things and part of the fire flow testing is we're going to look at what is going to be the maximum amount of water we can move to a certain point in our water system while still maintaining 20 PSI throughout the entire system. So when we drop below 20 PSI, that's when we enter a danger area for back siphonage into our water system. So we want to try to always maintain that strong positive pressure throughout the system so that we're not sucking water out of homes or other buildings when we are fighting the fire. The Fire Underwriter Survey, they also have, quick points about, where valves should be, where hydrants should be located in your system. And they also, start to specify what type of hydrants you should have in your system. So, one of the key things is that fire hydrants should be supplied by mains that are at least 150 millimeters or at least 6-inch mains as a minimum. And that at a minimum, they should have at least the 2.5-inch or 65 millimeter outlets on a hydrant. Now, if the calculation for your fire flow for your system that you go through with the Fire Underwriter Survey, if the calculated flow that you require is going to be greater than 5,000 liters per minute, that is where you need to be able to provide a pumper outlet on your hydrant. Now, once again, if your calculated flow is going to be less than that, it's 4,000 liters per minute, well, you don't need to have a pumper port, but it would be advisable to have one anyway. Now, this is the calculation that is in the Fire Underwriter Survey that we can use to calculate, what is the actual fire flow that I need at a certain point in my system. And it's based on the building that you're going to be trying to fight a fire with. Now, it looks pretty simple. We've got a flow, we've got a constant of 220, we've got a construction coefficient, and then the total floor area of the building in square meters that we are going to be possibly fighting a fire with. But from that formula, there ends up being, and I'm going to go through this point fairly quickly because it's not something that you would normally do you have to start adding in, okay, then my construction coefficient. What is the building that I might be fighting a fire? What is it built out of? Is it wood frame construction? Or is it a brick construction? And that changes the flow that's required. What's going to be inside the building changes the flow, right? So, is it a woodworking building where we're going to have lots of flammable finishes in it? Well, that's going to increase the flow that we're going to require. Is there a sprinkler system installed in the building? And if there is a sprinkler system, well, that will reduce the required flow that we need inside of that building. This is a big one, especially in the last couple of years. We've heard this one quite a bit. Is what is your exposure? So how close is your building to some other combustible building or material? So how close is the tree line? How close is the neighboring house? And if you have your homes packed in nice and tight together, well then we have to do an adjustment on the fire flow because of the danger of the fire spreading to other nearby buildings. Now we can add all those things together. Like I said, we've gone from that very, very simple formula we started with, and now we have to add in all these other increases or decreases depending on the very specifics of the building that we are looking at. And from that, we end up with a value. Now, after all that, the Fire Underwriters Survey also just tells you that, hey, we'll just give you a shortcut, right? If we're just looking at single or multifamily dwellings that do not exceed 2 stories in height, well, we can just use the shortcut formula. So generally for detecting or measuring fire flows inside of a system, we use 4,000 liters per minute as our benchmark because that is seen as a wood frame, 2-story wood frame building with exposure between 3 to 10 meters. So your neighboring house is maybe 10 meters off on the side of your home, and that's a pretty general way that homes are constructed. So once again, we kind of use that 4,000 liters or just over 1,000 gallons per minute as kind of our benchmark that we're looking for when we're doing a fire flow test. Now we also have to make some very final adjustments too. If the home, has cedar shake roofing, well, that's going to require a lot more flow than to try to fight a fire with our water system in those types of homes. So we're not going to go run through a worksheet. This is something I do if we were in class. We would do a worksheet for the building that we were located in and try to work out that fire flow. But as I mentioned, generally we just use that 4,000 liters per minute or 1,000 gallons per minute as our bench line. If we can get higher than that, we have good fire protection in our system. Right? If we're below that, well, then maybe we have to look a little bit more in depth, and if there's something that we can change about our system and provide better fire flows. Now, this is also goes back to our reservoirs that we have inside of our system, and this idea that a large capacity or large portion of our reservoirs are really just based around trying to meet these fire flows. And so we have very small amount of space inside of our reservoirs that is actually just used for domestic water use, right? And that's kind of the pump on, normal pump on, pump off. That's our operational storage inside of the reservoir. But the vast volume of it is used for that emergency or our fire storage. And that's where, once again, we're looking at having that 120,000 liters as a minimum in that emergency or our fire storage, right? We need to be able to not only produce these flows, but maintain these high flows for long periods of time. So we've gone through, possibly do some calculations, or we've just said, hey, we're going to use the shortcut. I want to see, can my system deliver that 4,000 liters per minute if required? So what we're going to have to do is we're going to have to go out and do some field testing and see what that actually is. So we're going to be using some hydrants. If you're looking very specifically for one of the buildings inside of your system, you're going to be using the hydrant that is located closest to that building. Now, the values that we get from this, we can extrapolate that data. We can look at things like, trying to make some changes to the water system infrastructure, maybe if our fire flows are not meeting those minimum values. So whether that means we're going to have a case to build a larger reservoir, or have a case to upgrade the water mains to a larger size, or possibly loop those water mains because we're not able to meet the flows that the Fire Underwriters Survey is saying we should have to meet. Now, one thing to be very clear here as we go through the next few slides here, and there's a handout that is in the available to you, is that when we're talking about the fire flows here, we're talking about the main capacity. So what is the maximum amount of water that we can draw out of our water system at a certain point in our water system? Now, if a lot of you have maybe done some hydrant flushing and you've put a diffuser with a flow meter while you've been doing hydrant flushing, that's great, really good information, and that's actually part of the fire flow test. But that is something we call the hydrant capacity. So, what is the normal flow coming out of a port of the hydrant when we open it up? Once again, for fire flow testing, we're going to look at what is the maximum we can take out and still maintain that 20 psi in the water system. So that is what the fire flow test is going to be. So to do this, we use a lot of the same procedures and equipment that you might be doing as part of your regular flushing, or part of your regular maintenance on the hydrants. But we still need to go through. We need to make sure we've got good planning. What are the hydrants we're going to flush from? Make sure we have all the proper equipment available to collect the data we need for the fire flow test. We also have to pay attention, and we're not going to be flowing water for long periods of time or large volumes of water, but we need to dechlorinate that. We need to make sure we know where that water is being discharged, so we're not flooding out someone's driveway, or making sure then we have that discharge under control. We also want to make sure we have lots of water in the reservoirs. So, is our reservoir full when we are going to do this test? Another key thing for the fire flow testing is if you do have a fire pump, the fire pump should be running when you do this test. As I mentioned there, we're only going to be running the flows for very short durations. We're to collect some data from our system. So this is the very, very simplified kind of diagram of what you are going to do to conduct a fire flow test. Is we need to use 2 hydrants as a minimum, and we designate those ones as the test hydrant and the flow hydrant. Now, depending on, in the handouts, there's another handout on how to do this test available to you. A lot of handouts will call the test hydrant the pressure hydrant, or the static hydrant, or the residual hydrant. It goes by different names. But this is the hydrant that we are going to add a pressure gauge to, and we're going to measure the pressure constantly at this hydrant while we are conducting the test. Now the flow hydrant, that one is the next hydrant downstream from our test hydrant or our pressure hydrant. And that is one we're going to have to add our flow measuring equipment to, right? So this is very key for this one. This is the one we're going to open up and we're going to start discharging water, but we need some way to accurately measure the flow that is coming out of that hydrant. So in its simplest form, this is what we're going to do here, right? We're going to look at our system and we're going to designate, okay, this here is my test hydrant, and the next hydrant downstream, that is going to be my flow hydrant. I'm going to go to the test hydrant. I'm going to put a pressure gauge on it. I'm going to open that hydrant fully, and I'm going to measure what is the static pressure at that test hydrant. Then I'm going to go downstream and I'm going to go look at the flow hydrant, and I'm going to start documenting some information. You know, what was the size of the water main that is going between these two hydrants? What is the inner diameter of the hydrant nozzle that I'm going to use? You know, is it a 2.5-inch nozzle, or is there some other manufacturer and it's a slightly different size? I'm going to show a diagram here later, but we're also going to look at, you know, the hydrant nozzle. How smooth is the transition inside of the hydrant going to that nozzle, right? Is it a nice curved edge, or is it a harsh 90-degree sharp edge between the inside of the hydrant and that nozzle? So I need to record that information. Then what we're going to do is we're going to add whatever flow measuring device we have. So if it's a diffuser that has a pitot on it, or if we're going to use a handheld pitot, we're going to attach the discharge tube to the hydrant, and we're going to slowly open that flow hydrant, and we're going to wait till we get it fully open and that we get the maximum flow coming through that port that we're measuring the flow from, and we're going to take a reading. So once we have that reading of the flow, we also need to go back to that static pressure hydrant or that test hydrant we had and measure what the pressure is at that hydrant.
It is, yes.
I'm gonna have someone else's audio here too. And then we calculate then we can use that information and we can calculate the fire flow at 20 PSI. So once again, what would be the maximum amount of water I got out of that hydrant and still maintain 20 PSI in my system? So what we're looking at here is, you know, if the fire department came and hooked up, you know, hoses on both ports of the hydrant, or they hooked up to the pumper port of the hydrant, and they were just trying to go just withdraw as much water as they could, what would be the maximum amount that they could possibly take? So this is some diagrams of how to decide which one is the flow hydrant and which one is the residual or the test hydrant. Now for most systems, if it's a straight line, it's nice and easy, right? You do the residual hydrant and then you do the flow hydrant as the next hydrant downstream from the residual one. Now, if you've got a tease or you've got bends, you've got looped systems, it might get a little bit more complex. But the general rule is that you want the water to be flowing past the flow hydrant, sort of past the test hydrant going to the flow hydrant. The other thing that you can do if you have a loop system is you can run the test in two different directions. So, you know, you can open up hydrants on both sides of the hydrant that you're measuring the pressure from, and you can compare the results. And the results should generally be close to one another, but it's a good way to also confirm what the flows are that you're getting with your system. Now for the taking of the pressure, this one, is very, very important. This probably, like any type of calculation, you have to put good data into the formula to get a good result. So the more accurate that you can measure the pressure, and we're going to show later here, the more accurate that you can measure the flow coming out of the hydrant, the better your results are going to be. If you are just using a direct read pressure gauge, then the more accurate that pressure gauge is, the closer it is to what the maximum pressure you're going to achieve, or the minimum pressures you're going to achieve in that system, the better off you are. So once again, if your system in your normal pressure in your water system is only 60 psi, then using a 0 to 200 psi pressure gauge is not going to give you a great accuracy for your readings. You're going to want to get a pressure gauge that is a little bit tighter there and a little bit closer to the pressures in your system, right? If you can get a 0 to 100 gauge, that one will improve your accuracy of your readings. You also, if you're doing this with two people, which is very common, is you'll have someone standing down at the hydrant that's recording the pressure, and you are going to be recording the flow. And once you have taken that flow reading, you need some way to alert the person down at the other hydrant that, hey, it's time to take your pressure reading again. And if you don't have two people, or you want to even improve your accuracy a little bit more, one of the things you can look at is adding in some sort of a pressure logger onto your test hydrant. And that's what this picture is showing here. This is just a pressure measuring device that you can add onto the output port on the hydrant, and then you can just program it to say, hey, every 1 second, every 5 seconds, every 10 seconds, whatever, I want you to take a pressure reading and log it. And then you'll be able to go after your test and download those readings off that instrument and see what the pressure drop actually is when you are flowing that hydrant. So this is someone, now this would be in a larger municipal type system, and they are at the flow hydrant, and they are reading the flow coming out of the hydrant. Now, one of the things for this test is that when we flow the hydrant, we must see a pressure drop in the residual or the pressure hydrant. And we want to see a drop at least 25% of what that static reading was for the test to be considered a valid fire flow test. So once again, if let's say your residual pressure in your system is 80 psi, when I open up the fire hydrant, I want to see that pressure in that residual hydrant. I want to see it drop to at least 60 or lower. If it doesn't go below 60, then I need to increase the flow. The higher the flow I can get, the more pressure drop I should see. So I might have to open up a second port on the flow hydrant. I might have to change my setup and maybe flow 2 hydrants at the same time to get enough flow to see that pressure drop. Now, this is generally not a problem for most small water systems. This is something that larger municipal type systems with very large pipes and large reservoirs have to really worry about. And they might, once again, have to flow multiple hydrants to try to get that pressure drop to occur. So this is a diagram here showing, again, as part of that calculation, we need to record what is the type of configuration of the nozzle that we are flowing the water out of. So it's usually pretty simple. You can, after you take the cap off of the hydrant ear there, you can just put your finger in and just feel. Most modern hydrants that you probably have in your system are going to have the smooth rounded outlet, right? And you'll run your finger in there and you have a nice curve between the inside of the hydrant and the output port there. Now, if you do have one that has a very sharp or 90-degree bend inside of the hydrant going to the port, you do need to note that because you're going to use a different or a change in your formula there. And this is just related to the flow pattern that the water has to make. And if the water has to go around that very, very sharp 90-degree bend, we have some large friction losses to go through those 90-degree bends inside the hydrant. And that is going to mean that we're going to get less flow out of those types of hydrants. And that's once again why most modern hydrants have a nice smooth inlet going from the inside of the hydrant to that outlet port. Now, measuring the hydrant flow, right? We're going to have the hydrant is open fully. If we've got a fire flow pump, the fire flow pump is running. We're trying to get the maximum amount of flow that we can out of here. And we've got to have some sort of way to accurately measure that flow. So whether we're using a flow gauge in our system, we're using a pitot tube like what's shown in this picture here. We can also use a residual pressure gauge, but that is not a very accurate way to do it, but it can be done. Whatever type of flow gauge you are using, make sure you are following the manufacturer procedure for that type of flow gauge. And this is just now another one with a diffuser that has a pitot attached to it. So this is a very, very common way to measure the flow. And this is a very accurate way to do that, right? Once again, though, make sure that your hydrant is fully open, fire pump is running if you have one, and wait for the flow to kind of maximize and take your reading. Now, you might also see on your, if your diffusers, you might see a chart like this, or this got just supplied to you from the manufacturers. And this is just showing what the differential pressure you should see on a fire hydrant depending on what the flow happens to be. So what you can do is, I'm going to go back a slide here to this picture, is the hydrant that you are going to flow from is you can put a pressure gauge on the opposite side that you are flowing from. And you can measure, what is the static pressure when I have no flow, and then what is the residual pressure in this hydrant when I am flowing at the maximum. So it's also a good way to check that your pitot is working. But if you didn't have the pitot shown in this diagram, this is a way you can try to do this measurement. So you would look, once again, let's say my pressure when I started the test, when it was static, was 80 psi. And when I was flowing the hydrant at its maximum, the pressure was at 40 psi on the opposite ear of that hydrant that I was flowing. I could look at the chart, and the chart would tell me, well, my flow is 961 gallons per minute because I had a 40 PSI difference between what I started with and what the pressure was reading when I had the hydrant fully open. So at this point on the fire flow test, we have two pieces of information, right? I've got my static pressure in my system when there was no flow, and then I have a residual pressure in my system when there was flow. So I can use those two pieces of information with the diameter of the water main, the coefficient of my discharge, so what the hydrant, the port looks like, and now I can calculate out what would be the maximum flow that I could get out of that hydrant. Now I know this formula looks very complex. There are shortcuts to get around that, and we'll show you that very quickly here. This is if you don't like working in metric and you want to do your test in gallons per minute and you want your answer in gallons per minute. It's the same formula. We're just changed around between metric to imperial units. And once again, I know it looks a very, very complex formula there, but we'll, like everything, there's a shortcut way to get around this and not have to worry about doing the math. I'm going to skip by that, and we won't do an example here, just to make sure we save time here. Now, when we get the data that we've collected from our fire flow test, we can enter that into a spreadsheet, and we can maybe use this to calculate out predicted fire flows for later events. If we're working with an engineer who maybe wants to look at doing some hydraulic modeling of our system, this would be great data to give them to help out their modeling system. Now, this is what we do with the results. Now, this is a very simplified graph that we have. But once again, hopefully we remember back to grade 5 geometry. And when we did graphs, one of the things we got taught was that if at any time that you have 2 points, you can draw a line, right? So in this test here, for this one example, right, we had 2 points of data. I had 0 flow, and I tested the fire hydrant, and when there was no flow, the static pressure in the system was 75 PSI. So that is 1 point of data. Then we conducted the test, and when we conducted the test here, my second point was down here at the bottom of the solid red line. And when the flow was about 4,500 gallons per minute coming out of the system, the pressure was about 28 PSI. So if I have 2 points, I can draw a line. And now when I draw my line, I can extend that line and see where does that line cross the 20 PSI limit. And once again, that is what our fire flow test is we're trying to say, what is the maximum flow that we can get in the system and still maintain 20 PSI. So in this case here, this one happens to cross that 20 PSI line at just under 5,000 gallons per minute. So, very large system, lots of flow coming out of the hydrants here are available for us for this system. Now, for your most small water systems, you're not going to end up with those numbers being that large. But once again, you can use the same sort of graphing to try to see what those values that you're able to achieve. Now, I'll show you some shortcuts when we get to the end of the presentation here. I'll just save me from jumping back and forth here. Now, the other thing that we can do once we have finished the fire flow test is that the Fire Underwriter Survey, they actually have color codes that you should either paint or identify your hydrants with, depending on the flows that you have available. And this is just an indicating to the fire department that is coming to serve your neighborhood or serve your small water system. This indicates to them really quickly, hey, you know, at this hydrant here, I'm not going to be able to get a lot of water from because it's painted, the top and nozzle colors is painted red. Or they show up and they're like, nope, this is a light blue. We know that this hydrant, we're going to be able to get a lot of water out of this hydrant. So, you know, we can hook up to a pumper port and we can hook up our pumper truck to this hydrant here because we're going to have lots of water available to us at this point. Now, this is something that I don't see a lot of small water systems doing, is color coding their hydrants. And this isn't the body of the hydrant. We're just talking about the very top cap of the hydrant here. But if you start keeping your eyes open when you're in some of the larger municipalities, you should notice that you're going to start seeing this where, you know, hey, their hydrants are all red, but, you know, in this neighborhood, the tops of the hydrants are blue. And I moved on and, you know, the tops of the hydrants in this neighborhood are green. And that's just, once again, a way to quickly identify to the firefighters what type of flow they can expect from the hydrant when they hook up to it. So, and this is just some pictures of different hydrants and what we're going to do for the color coding. So once again, it's not the body of the hydrant that we're looking at, it's the top cap of the hydrant that we are painting the color that corresponds to the flow that is available. And if you don't want to paint the hydrants, another thing that is very popular is to use hydrant flow identification discs. So you can buy them in the different colors that you need, and then you can just attach those onto the side ports of the fire hydrant. So what you end up with is something like this diagram here, where they've done both actually. They've painted the top of the hydrant the proper color code, but they've also added the disc to the side port. I'm going to now quickly show you some of the shortcut stuff here. Whoops. So this here, one of the main companies that you might be buying diffusers from is called Hose Monster. So this is their hydrant flow test calculator that they make available. If you do a Google search for any, and all you do is type in hydrant flow test calculator, there will be a never-ending list of different ones you can use. I find this one is the best one that's readily available. And once again, rather than doing that complex calculation when you have your data, you can go to their website and you can just enter your data into their calculator. Now, it's going to come out in gallons per minute, and they're going to use PSI. So, you know, make sure that you take your readings in that case. So this example here that I put in here, you know, I said, hey, I've got my small water system. I went and I measured the static pressure. You know, before I started flowing water, it was 60 PSI. Then I went and I opened up the hydrant. I opened it up fully, and I got 600 gallons per minute flowing out of my flow hydrant. So that's another data point I've got. And then I called down the road to my coworker and I told him to read the pressure at that test hydrant again. And he looked at it and he says, yeah, okay, while we were flowing, we had a residual pressure of 40 PSI. So I've gotten all my data points that I need for my fire flow test. I've achieved a drop of at least 25 PSI, so this is going to be a valid test. So now I put the data into the calculator. I can press the calculate button, and I can scroll down and they give me the data for my hydrant here. So in this case here, I'll make that a little bit smaller so it all fits. They give me the graph and they give me the calculation. So they say, well, from the data you gave, yes, you got the right pressure drop, but this is going to be a orange coated hydrant. And at 20 PSI, the maximum you're going to get out of that hydrant is going to be 872 gallons per minute. So for that hydrant, one of the things I would look at right away is, and then I could go back to the Fire Underwriter Survey and I would be able to look and they would be able to tell me that, you know what, for a single family 2-story home, the minimum is supposed to be 1,056 gallons per minute. So I'm not meeting those minimum fire flows that are required to provide fire protection in my system. So at this point here, I would have to start looking at, okay, how am I going to change my system, right? Am I going to have to install a fire flow pump? Do I need a larger reservoir to give myself some extra capacity and maybe have that reservoir be a little bit higher that will give me more pressure in the system, which will increase my flow? Do I need to increase the size of the water mains? Or do I need to loop my system to get more flow at this point? And that is the key thing we are looking at for our fire flow testing, right? So we're trying to do two things. One, are we meeting the minimum requirements for the Fire Underwriter Survey, so that we're, and this affects people's insurance rates in our water system. And then we're using that information to help us plan for future expansion or future changes to our water systems. Now, the only other thing I did have to show is there are some handouts. Once again, oops, why is that one not coming up? Good. One second. Hopefully that has popped up for everyone there. This is one of the handouts to try to show the difference about what you're doing as far as just maybe your regular hydrant maintenance and measuring the flow while you're doing that, compared to what we're talking about here. We're doing this main capacity flow test, right? That's what the fire flow test happens to be. Now there is, they'll make my presentation available to you if you want to follow that. I did also add some handouts that have been in some of the trade magazines. They also run through, once again, how to do this test, what are the measurements that you have to take, and how to do the calculation for that test. This is something that is recommended that all systems do at least once every 5 years, or any time that you have made any large changes to your infrastructure in your system. So if you've installed new pipe, or you've changed the flow pattern by closing off, making a loop in your system, then you can go back and check how those changes that you've made have affected your ability to fight fires with your system. Now that's all the information I have at this point. So I'll turn this back over to Satwinder, and again, just try to see if you have any questions about what we presented here today.
Thank you so much, Scott. Yeah, I'm just going to wait for the questions to appear and then I'll read them to you. We are working with EOCP to make sure that they're updated about the change in the topic of the presentation, so everybody receives their CEUs. We'll make sure that's done. While we're waiting for questions, I have a couple of announcements. So we also offer free courses, and we are building the amount of courses we will have available for free. And they're available on a continuous basis online. So we have launched 2 courses. One is the Emergency Response and Contingency Plan course as to how systems should go about building their ERCP, and the course helps you prepare an ERCP. And then we have also launched the second course. It's an exam preparation course. It's a small water system exam preparation course. And so please enroll in them, and they are offered for free, and they're available for continuous enrollment. All you have to do is create an account and go ahead and take courses. And more courses are coming up. We are hoping to launch a course in water sampling and water quality monitoring, and disinfection and CT. So those courses are also coming forward soon. So, so keep on visiting the website and so on. Okay, so we have a question, Scott. The question is from James. If we have issues with iron and manganese, should we be pre-flushing or purging the hydrant before attaching the pilot?
Pedo. Yeah. James, yes. So that's a great question. Yeah, I would suggest that you flush the system first. Try to remove as much debris out of the system first before you are doing the test. Yes.
Okay. Should it be flushed for a certain amount of time, or just still you see the water clearing out?
Yeah, this one's for the test. I would say you'd want to maybe run it till it's clear, while taking into consideration the capacity of your system. Now, one of the issues is that you know, in the case of the firefighters showing up in an emergency situation, they are not going to flush your hydrant, right? They are just going to hook up to it and go try to deal with the emergency right away. So that if you do have lots of iron and manganese problems, that is just something that you're going to have to convey to the fire department also, that services your area, and that they should expect that the water is going to be dirty coming through their hoses for some period of time.
Okay. We have a question from Jeff. Please address water hammer when closing hydrant valves.
Yes, Jeff, and great comment also. As with any time that you're doing any type of flushing, is you want to make sure that you are operating your valves in a slow manner, right? Slow but steady manner. So we are not turning on the hydrants really quickly, and we're not shutting them off very quickly. Yes.
Okay. So just, yeah, like everything, whenever we open something, it has to be done slowly. Okay. Yeah. Back to James again. Does it matter how far away from the fire pump the test hydrants are? For example, PRVs or pressure zones?
Yes, James. So this is why you want to try to go through your entire system and doing this testing, because it really does matter how far away from that fire pump you are. The further away from the fire pump you are, the more friction losses you're going to get in your pipe, and that's going to mean you're going to get lower flow the further you are away from the system. So you definitely, at least one of your tests should be at the very, very end of your system. You want to be as far away from the fire pump as possible, right? And that's going to kind of show you what the minimum flow you are going to get out of that system. And your other ones for PRVs and things, once again, you're going to see the same thing, right? Where your fire flow might change quite dramatically from the upstream side of the PRV, where you have a very, very high pressure, and then the first hydrant you have on the downstream side of a PRV, you might have very, very little flow available at that hydrant because of that restriction of the PRV. So yeah, that's where it's very important to, once again, every 3 to 5 years is to go through the entire system and do these flows at all the hydrants.
Okay. So if your community is going through a growth period, should that time be should be done more frequently, or?
Yes. So the 3 to 5 years is the recommendation if your system has not had any large infrastructure changes. And anytime you do any large infrastructure where you maybe upgraded the size of the pipe in your system, or you've closed off some loops or added in a new subdivision and a new section of piping onto your system, you should redo those fire flow tests.
Question from John. Why is the pressure drop of 20% important? I know you said in your presentation 25%, but yeah. So why is that pressure drop important?
John, that is people who are much smarter than me and work in stats. That is what they have come up with as their benchmark to try to determine that the data is going to be able to make a good line, right? So when you're extrapolating data like this with a line, if your 2 points are very, very close together, that just increases the error that you're going to get when we're extrapolating that data further away from those points. So by making sure we have that 25% drop in the pressure, it's just a way to guarantee our 2 data points are a little bit farther away from one another, and then we can extrapolate those data points.
Okay, this is just a comment, and I don't know if you can further comment on this, Scott, as well. Building sprinkler designers prefer high pressure, like up to 150 PSI, to minimize pipe sizes.
Yeah, and so Jeff, and that we show that kind of in your distribution system with the idea of having that fire flow pump, right? And also in the slide there, I know it kind of maybe went through it real quickly, but it is this idea is that if you get higher pressure, there's a direct relation between pressure and flow. So at the higher pressures, we can get more flow. And your comment is exactly it. And when we get to very high pressures, well, then we can lower down the pipe sizes because we're able to get so much flow between those in those smaller diameter pipes at those higher pressures. Yeah, and once again, if your system, it is one of the solutions, like if your system is not meeting those minimum fire flows, one of the quick things you're going to look at is, can we increase the pressure in the system and then meet those fire flows then?
Yeah. Question from Mark. I was wondering how different the residual pressure would be if the residual pressure was tested on the same hydrant you're flowing. I have only one hydrant that is on the lower section of a pressure zone. No other hydrants nearby to check residual with a gauge.
For your, Mark, for your system, what we would do then is we would use, rather than using the hydrant, we maybe, is there some other way we can measure the pressure in the system away from the hydrant that you're flowing? So can we put a pressure gauge on a hose bib on a house and see what it drops to there? That's going to be maybe the best you can do in that case. Is there a pressure gauge on a PRV or on the main somewhere that we can measure that drop? But yeah, that's gonna, you do need to be able to measure the pressure somewhere else other than the hydrant that you are flowing though. So yeah, your situation might be a little bit difficult to get that one, to get that second data point.
Question from Brian. I was surprised to see chlorine residual as a consideration in flushing. Is this a reality in the field?
So Brian, it is, you know, even though we're only flushing for a very short period of time, you know, any time that we are discharging large volumes of water out of our system, we do have to dechlorinate that water as it enters the environment. Yes. So that is hopefully a reality in the field for you.
Okay. And Scott, we're looking forward to having you back about talking about, you know, flushing with chlorine. What does that mean, and how to handle the water after the flushing and how to dechlorinate. I'm looking forward to that presentation from you. I don't think you knew you were going to do it, but I have you already listed for that. So
Good.
Question from Jeff. Please notify the water system operator before testing to avoid pressure drop and main break alarms.
Yes, and you know, notify everyone in the system. That's what we're doing. You know, you want to make sure everyone's aware that you know, if they're having a morning shower, that the pressure is going to drop. But also all the same warnings that you normally send out anytime you're doing your water main flushing, because you know, you might also be stirring up at the same time some sediment in your pipes. So you know, people might notice that also at their taps. So really the same notification you do when you're out doing your regular yearly system flushing, you want to send that out again anytime you're doing hydrant flow testing. Yeah.
And then when you're putting everything back, you're desanitizing and all that kind of stuff anyway, right? Restoring everything back to normal. Okay.
Yeah.
Question from James. Does water in distribution system counts towards the fire flow capacity? So all of your total storage counts towards flow capacity?
Good question, James. And I can't give you an exact answer. You know, at the end of the day, it would have to be included in to try to meet those minimum flows. I would have to look at the language again a little bit more closely in the Fire Underwriters Survey. My initial response is that I think they specify that is supposed to be in the reservoir, but you know, I'd have to look at the language in that Fire Underwriter Survey a little bit more deep to give you a true answer for your question there, James.
Scott, do most small water systems have this capacity for fire flows? Because they don't really.
No.
Okay.
No, so we see this as a big difficulty in a lot of small water systems, and especially with a lot of very small water systems, is they just do not have the reservoir capacity, or you know, their water mains are, you know, they put in 4-inch water mains and they're just not able to achieve those fire flow capacities. So, you know, I just did some fire flow testing in a small water system, and that was the case. Even though they had 6 fire hydrants going through this small subdivision, it was all 4-inch water mains serving those hydrants, and we were not even close to getting to those minimum fire flows.
Yeah, I don't see any more questions on this. There's another one. A comment from Jeff. No, you can't include water in the pipes for capacity, as this would drop your residual system pressure below 20 psi.
Yeah. So, and once again, I'll look into that a little bit more deeply and have a better answer then. Yeah, perfect. But thanks for your comment, Jeff. That makes total sense.
Yeah. I was just wondering, like, if you consider total storage, but I think your slides just refer to storage in your reservoir for this. So
Yes.
okay. Okay, I don't see any more questions come forward. But if you do have any more questions, we'll make sure that we'll forward them to Scott or try to answer them to our best to our capacity. This webinar and Scott's slides will be posted on our website in a day or two. And then, of course, the certificates will be issued to the topic we presented on today. And our next webinar is coming up Tuesday, June 17th. And the topic is reliable and resilient water systems. I know that is becoming, it's an upcoming and new issue to make sure that we are building these and operating these our systems in a sustainable and reliable and resilient ways, given that the threats we face from climate change and so on. Scott, I can't thank you enough, as usual. So thank you so much for stepping up, and what a great topic and what a helpful topic for all small water systems in British Columbia. So thank you so much.
Thank you. Thanks, everyone.
Thank you,
Enjoy out there.
Thank you for attending, everyone. Bye.